my name is Brian and I'm here to hack on TigerBeetle. So, on this stream, I am working on the adjusting my audio Rust client for TigerBeetle. TigerBeetle is a high-performance financial database written in Zig. It's got clients in almost every language you could want except for Rust and also upcoming Ruby, probably. On the stream, we've been doing this since November. We're writing that Rust client. Last month, we we landed the initial PR. It's feature complete, but not production ready. Right now, we're in the process of writing the tests, then writing the docs, and then we can publish to crates.io, and everybody can use this beautiful piece of software, piece of art that we have created. It's been a while since I streamed. I gotta admit, y'all, I'm just feeling the anxiety about the streaming. I mean, I have anxiety about everything, but I've been feeling resistance to getting back on camera recently. But we've broken the seal and we are ready to rock. So today we're going to be writing tests for the TigerBeetle Rust client. And I kind of just need to, push through and get it going. So let's just get started. And as I said, it's been, weeks since last time we worked on this, so don't know exactly what's going on here. This is just looking at my workspace on this machine. This is stuff relating to compaction. I was working on an optimization to the LSM tree and spent weeks on that, but it's not really gonna pay off. So this branch I'm abandoning this branch. And now we got to find the branch that contains our Rust client tests. I'm guessing it's the one called Rust client-tests. Let's check that out. This branch again is old, so we're gonna have to rebase. You can see here I was in the process of just hacking, so we'll go ahead and squash all of this onto origin main right here. So I'm just going to say git reset origin main, and then there's all of our tests. Commit all those again. Now our history is just one commit. We'll fetch and then rebase onto new main. Git rebase origin main. And there's our new up-to-date history, May 27th. All right, first thing we're going to want to do, I think, is just go remember how to run the test for the TigerBeetle client. The TigerBeetle clients are all in source clients. Ours is in Rust. Here's all the stuff we got in this directory. I think we just run cargo test -- all, and that'll get us there. Let's see if these tests pass. You can see it's rebuilding TigerBeetle because it needs a bunch of, it needs a library called tbclient written in Zig. So when we build a TigerBeetle Rust client, it also builds TigerBeetle, or at least the TigerBeetle client library. Let's go look at our tests and see. Let's just kill this Emacs and start fresh. Source clients Rust. I think everything we care about today is going to be in this test.rs file. You can see here we left ourselves some to-dos, which I am thankful for after several weeks, because I don't remember at all what we were doing besides writing tests. All right, I'm not going to look at these to-dos yet. We'll come back. Let's just first look at the code and remind ourselves what's going on here. But here's our test run. So the test looks like it worked. You can see our tests spew a bunch of junk to standard error. That's kind of surprising. Why are we spewing all this? have to think about that. Every one of our tests spawns a TigerBeetle server. And the server, we're apparently just letting the standard error inherit. And so the server standard error is just going all over our test output, which is not amazing. We might fix that up for final pull request. All right, here's some random number generation. This is because we're not using the rand crate, we're just using the standard library, and we're stealing some random numbers out of the hash tables in the standard library. So we have a test harness, a custom test harness. This runs the server. And yeah, this just runs the server. Keep some mutex. Our tests in this crate are all serialized because running TigerBeetle is, very big. TigerBeetle is massive. So I don't want to put a TigerBeetle on every core on your computer. So we have our smoke test. And then last time we wrote several more tests. Testing the constructor, destructor, close. Lots of accounts. Oh, this is the helper. 0 events, result. Okay. Multi-thread. So we're doing a test that this type is sendable to across threads. We put the client in an arc. We wait for all the handles, pull the client back out of the arc and close. So typical multi-threaded scenario. Just making sure that the types all fit together and that it's possible to write multi-threaded code with this client by sharing it in an arc. Okay, that all makes sense. Before we continue, I had one thing I wanted to check about the source code to this library. I woke up in the middle of the night a few weeks ago just panicking that I had leaked the unsafe client handle. And I just want to go back and check that real quick. So you can see here, our Rust client just contains a owned unsafe pointer to the inner TB client handle, this thing. So this is defined by the TB client zig library that our Rust code is bindings to. And this gets allocated by the Rust code, and the Rust code is responsible for freeing it. And I just had this suspicion suddenly that I had forgotten to free this. So let's take a look real quick. You can see here is where it's allocated, and then so we allocate this using the safe box function. So this is a box of a TB client, but then we say throw away the box and just give us the pointer to the inside of the box. And so the way you free this is at some point you turn it back from an unsafe pointer back into our Rust box again, and then the destructor takes over and it all works. But if we look, our destructor for this type is fairly complicated. So it always defers to close, and then close does some mildly tricky stuff, not super tricky. So in another thread, what's going on? Okay, so here you can say we take that inner unsafe client and we take it and replace it with null. So the handle inside of our client type here becomes null. And now we have the only unsafe pointer to the client. We send it to another thread to call the dinit function. And then you can say right here, you drop it. So it's all as expected. Turn it back into a box and drop it. It's interesting, I wrote stood mim drop here. And then here I just wrote drop. That's pretty strange. Not a big deal though. Okay, so let's look at these to-dos. Can we test that we use the client handle after destructor? So the internal unsafe client handle is shareable. And there's no type system mechanism to ensure that you don't call the destructor on one thread and then use it on another thread after the destructor is called. So this is a note to just test that, but structurally, we have made it impossible for this scenario to ever arise because the Rust, we've set up the type so that it's impossible to destroy this type and then reuse the client handle afterwards. So I don't think there's anything that we can even write a test for here, because I just showed you that, like, you call drop on the client. So the client has the only, in Rust code at least, the only unsafe pointer to this interior handle. And when client goes out of scope, it calls drop. And client can't go out of, like in our test case, our multi-threading test, we put it inside of an arc, so that arc is an arc of a client. And this client can't be dropped until all the references to this arc are dropped. So once this is called, there are no other arc references to the client in a multi-threaded case. And then this close gets called. And by the time this TB client dinit is called, there are just no outstanding unsafe handles here. So it's just not structurally possible in the Rust code base. Other clients will have this problem where you can have, like in Python, you might have references to the client and the client gets destroyed and there are still outstanding references that has to be handled. But in Rust, it's just not possible. At least with the clever way that we have written it. So I just don't think there's anything to do on this test case. Call request, but don't await. Okay. So this is an async library. And you might create a client, then fire off many requests without awaiting on them. So you fire off 10 requests and get a future back that represents the result of that request. Maybe we stash those futures in a vector and then come back to them later and wait on them. And that's really what we want to make sure is possible. We basically want to make sure the type system allows that. Like the library definitely allows you to have multiple outstanding requests. But we want to make sure that the async type code that we've written allows you to fire off multiple requests concurrently. So that should be, pardon me, relatively straightforward. I'm going to put some of my previous code over here to crib off of on the right-hand side. Then on the left-hand side, I'm going to write a test concurrent requests. Let me see how I'm naming my tests. All right, I'm not prefixing them with the word test. So just concurrent requests. And I think my tests here, sorry, I should be referencing the right-hand side of my screen. Returns an anyhow result to do. Just notice this, pardon me, congested today. This stray import right here. Imports all want to live up here. I think the stream should be pretty fast today. Throughout this series of streams, I've been saying I was going to do the whole thing on stream, but some of this final production polish is going to be a little awkward. There's a bunch of docs to write, and I'm pretty skeptical about writing docs on stream. You know, could be instructive, but also very hard to, it's thinking and streaming and talking is already hard to do at the same time. Like writing and thinking and streaming and talking seems like a real uphill battle to me. I've never actually seen somebody like do creative writing on stream. Maybe people do that. And let's see, how do I want to do this? So here we had a bunch of join handles, take num threads. I think we just create a vector of something and we'll stash our futures into them. Should be fine. Let mute. Results, responses equals a vec of something. And for 0 to 10, doesn't really matter as long as it's more than 1. We're going to submit some requests. this looks promising right here. Just copy this client, create accounts. Yeah, exactly that. All right, and we're not going to await this future here. And I called this vec responses, and I called this thing results. Let's call it response. And then responses.push response. So now, all these futures here, these responses, these are futures of some kind. They all capture at least the client. Let's go look at the types. Let's go with the type signature for this create accounts method. Yeah, you can see that's below that's underneath my face. You can't see because my face is in front of it. Create accounts returns a future. The self has a named lifetime because the self contains that unsafe handle, and we want this future to basically lock that handle, or else we could like create a future, destroy the client, and then we're still waiting on the future result from that client, and it just seems wrong. So we've structured this so that the response future captures the client's lifetime. So that'll mean you can't call drop on that client, or you can't call close on that client while you have any outstanding requests. And hard to test that because it's like a negative test. It's a test that something doesn't compile. The way we would want to test that is to make sure that you can't call create accounts, hold the future, then call drop on the client, and then resolve the future. That shouldn't be possible. But writing that it's a compile fail test. And writing that test is pretty awkward in Rust. You can do it in duck tests, but you can't do it in regular tests. You can't write a test that says, try to compile this and ensure that it doesn't compile. Anyway, so this vec contains references. And that's always, a tricky situation as far as types go, because there's a bounded scoped lifetime on that vec now. It can't outlive certain things. Something like that. Anyway, let's keep moving. So after we create all these, let's make sure this actually tests. I'm going to say cargo check test, maybe? Tests. There we go. All right. That's a strange mistake. Just forgot the word in there. Yeah, need a OK down here. Okay, so that all type checks. That's good. You can notice we didn't have to type annotate this because it inferred from the push. And down here, you can say for response in responses. I think this is the only test we need to write, really. So we might be finished with the stream pretty fast today. For response and responses, let's go back to our tests and crib off whatever this was. Is this right? Result. No. So each one of these responses needs to be awaited, and then those responses also contain a vector of things that we assert on. So we're going to say let response equals response dot await question mark. We're going to await for the future. Then we're going to clear out that result. The result should always succeed in this case. And now we say for result in response. Kind of awkward naming, but whatever. All right, I think that's it. Let's see how that goes. Await only allowed inside async functions. So here we say block on. There's no runtime specific code, so we don't need to use Tokyo here. We're just using block on from the Rust futures crate. There's no, yeah, we don't need Tokyo or any other Rust runtime. We're just going to block on this future. And then question mark it. Await only allowed inside async functions and blocks. Put async here. There we go. Now let's run that test. Test. What is this? Concurrent. Okay. And that looks plausibly correct. I only see this one warning here. We submitted 10 requests, and I see this one request related warning saying one of our requests was slow. Maybe if we do it again, we'll see 2 or 0. Still one slow request warning. Interesting. It's consistently one slow request, but we did do this 10 times. I'm just kind of sketched out that maybe this is only submitting one request, but the code looks pretty clear, like it is sending 10 requests. I don't know. Anyway, I'm going to assume that's correct. No, not what you might want to hear. I think it's done. I think we're done with these tests. I'm going to just amend our previous commit. Let's say commit. I'm going to give it an actual message now. Client, Rust client, add tests. There we go. I'm going to say client Rust. I have no idea. Whatever. Now I want to run the static analysis stuff to make sure these tests will pass CI. So I'm going to do, what am I going to do here? I'm going to say cargo fumped. Cargo fumped. Oh, that's interesting. Formatting. A lot of formatting changes here. I wonder why. I wonder if maybe I upgraded Rust and cargo format changed a little. Or maybe I just added all of this in this branch. Anyway, that's all fine. Let's commit that. And cargo Clippy. Because we committed, cargo decided to do a full rebuild. I don't really understand this behavior. I only noticed it in the last 6 months or so. And because the rebuild here is so big, but seemingly every time you commit, I've noticed it in other projects too, so it's not just a misconfiguration in TigerBeetle. Like you make a commit and the cargo decides to do a rebuild. I feel like it didn't always do that. So Clippy's happy. So I'm going to push this. Force push that. What else do we need to do for the Rust client? I'm going to say the test suite is done. I'm also working on another program to test comprehensively all of the TigerBeetle clients. We have sort of a nascent testing framework in Tree and TigerBeetle called Vortex. And Vortex is similar to some of TigerBeetle's other testing frameworks that are kind of fuzzerish, and that it's just runs and generates a lot of random input. But where TigerBeetle's main test suite, Vopper, is a simulation, and it kind of simulates I/O, and it's not really running the full TigerBeetle. It's kind of like TigerBeetle, the library TigerBeetle, all like packaged up in a simulation testing framework. This new framework, Vortex, just runs the plain TigerBeetle binary and the standard TigerBeetle clients. And so it supports just running clients in any language because it's process-based. You just run a client driver. So you run the Python client driver or the Rust client Vortex driver. And so we should have like comprehensive testing for all of TigerBeetle's language clients sometime this year. But as far as the test suite for the Rust client, I'm feeling this is good. This is fine. Like it's not, this test suite for Rust is not comprehensive, but it's also a library. It's just a bindings to an existing library TB client, and that receives lots of testing in other ways from other client bindings. And this Vortex is going to test it too. So we really only need to test things here that are like Rust specific. So not a whole lot of tests here, but I'm pretty happy with how this is looking so far. I don't like, let's see, reload this buffer. I don't like the way the imports are ordered here. I think I can do that and Clippy will still be happy with that. Yeah. I just didn't like futures coming before stood. Yeah, I don't know what else to do really. So the other big things we need to do for the Rust client is write the docs. And writing the docs is very complicated because well, there's the crate docs we have to write. Let's just go normal Rust crate docs. That'll be fine. I'm probably going to do that on my own at this point because, like I was saying, I just don't feel good about writing and streaming. But also, there's a whole documentation system that is consistent across all the TigerBeetle clients. And I have to basically write a bunch of little snippets of code and snippets of test that all kind of feed into this documentation generator for the clients. And I think I'm just going to do that on my own. I'm going to be out of town for 4 weeks coming up in June for Systems Distributed, conference in Amsterdam, and also some other things. So I'm not going to be near my streaming studio. So I'm probably going to polish up a lot of the final bits of the Rust client just on the road without streaming them. Anyway, I'm going to submit this as a PR right now. Let's get that going. Yeah, we can do it. We can do it. All right, let's go over to our web browser. Make this fit the screen a little better. And I think I'm not logged into GitHub here, y'all, so I'm going to have to take a minute. Yeah, I've been logged out here. All right, I'm going to have to go find my 2FA device and log in, so give me 1 minute, y'all, and I'll be back. Just another second, y'all. We're back. Yep, I just had to go find my 2FA, log into GitHub. Really liking the lighting today. It's working out great. All right, so I'm going to submit a pull request for this. Yeah, you can see. Okay, let's look at the diff here. Okay, so all those things that were reformatted were things that I added in this PR specifically. Every time I submit a PR, gonna go look over everything in the GitHub diff, make sure it all looks decent. This all looks random U64, random U128, gotcha. Change that. It's mutex guard. I should add a comment here about why this is here. Yeah. Let's go to the code. It's not obvious why there's a mutex there. I mentioned it before. Let's go document it. Always good to read your diff and with the eyes of a reviewer before you hit send. All right, so prevent multiple tests from running in parallel. Tests run a full TigerBeetle. And that's a lot of resources. It's like a minimum, I think 2 gigs of disk space, maybe 2 to 4 gigs of RAM. It takes a lot of RAM to run a full TigerBeetle. I just started doing the Vortex project that I mentioned recently. And the first time I ran Vortex on my laptop locked up. And when it came back up, the file system was corrupted. And the easiest recovery was just to re-image the entire laptop. So now I'm running all my Vortex work on a gigantic VM in the cloud that costs $500 a month plus to rent. All right, that comment looks okay. Let's amend that. Force push. And continue pouring over our diff for our PR. All right, so now we have comments there. Random seed, random U64. Gotcha, okay. Test harness takes the mutex immediately. Test mutex is up there. Actually, this comment should probably be on the mutex, not on the mutex card. Let's go back and redo it. Let's go redo it. Force push. Let's go look at our diff some more. Server and client. This all seems okay. Port number. Harness serve. I think we get the port number from Sorry, I'm just zoning out a little here. Expand, expand. When we call serve, it returns the port number. The port number comes directly from TigerBeetle. So we let TigerBeetle pick the port it wants to work on. Take server and client, code, test code, and then just a bunch of tests, new tests. All right, this all looks very unobjectionable to me. Rust client add tests. Tests for the Rust client. And I'm going to assign this directly to MatClad, the Rust expert and genius. Done. All right. All right, this has been only 45 minutes so far. I think that might be good enough for just getting back into streaming. We accomplished a big thing. Still got to write some docs. Still got to publish to crates.io. But that's kind of it for the Rust client. Write docs, publish to crates.io, make some announcements. The docs are going to take a lot of work. Doing it on stream just doesn't seem very fun to me. It's going to require a lot of focus, right? Like really focused work to write the docs. I'm thinking about whether I want to do anything else here. We got some time. We have some time. There's another little CI thing we can do for the Rust client. I'm thinking we might go look at it real quick. Yeah, let's go look at it. So when we originally did this PR, I forgot to do a little bit on the CI. So I'm going to go check out the main branch again. And basically, the thing that I remember that I forgot to do is I don't think I set up the full test matrix for different platforms. I think we're only running Rust client CI on Linux. And it was discussed on the original PR, and I just kind of forgot to do it. Workflows, CI, Rust client, Rust. All right, so here's our matrix. Rust 1.84, Ubuntu. And I think that's the only Rust here. Let's see what other Rust code is in this. CI config. So if it's Rust, we assume Rust exists. We set it to the default to the version in the matrix. We say rust up component add, add Clippy in Rust format. And then all the rest of the test code is in scripts written in Zig. Let's go look at those real quick to make sure. Probably right here, ci.zig. This is the Rust client directory. Every client has a little CI script that feeds into the main CI script. You can see our test is just this stuff. There's nothing platform specific here, which is what I'm looking for. Nothing platform specific that we need to worry about. So I think the only real thing to do here is just add more configurations to the configuration matrix. And you can see we're also testing only on Rust 1.84. And it could be nice to make sure we support something earlier, but I think for now, until somebody comes to us and says we're not supporting their version of Rust, there's not a whole lot of reason. I mean, it would be nice to know, like, what is the minimum Rust we support? But 1.84 is good enough for now. So I'm going to copy this, and just everywhere I see a Go, I'm pairing Rust up with Go here. So I'm just kind of like cribbing up all along the way. I'm cribbing off of the Go client. So every time we see Go, we're going to put some Rust in. That sounds kind of nefarious. out of context. It's going to hunt down all the Go and replace it with Rust. All right, so there we have Rust on Windows. And then this is limited matrix for Mac OS. So we're not testing everything on Mac OS. Doesn't matter too much for me. I have high confidence that this code will work on Mac if it works on Linux. There's nothing in our Rust that gives me warnings about Mac. ARM, similarly, like the Rust code is CPU agnostic. I don't expect it to have any problems on ARM. But again, ARM is limited. Mac is limited, ARM is limited. Well, so I guess the only thing here we're doing is add a Windows runner. That's an easy thing to do. So the diff here, git commit CI, add Windows runner for Rust client. Git push CI Rust Windows. And we'll go do a PR for that. Let's do a PR. What is that? Interesting. Okay, compare this pull request. Make some excuses here. I don't add Mac or ARM because their machines are limited, but also don't expect any problems there. I'm saying I don't expect problems there, but there are like issues with things like dilib naming on Mac OS. But we don't actually link to a dilib, we do static linking for Rust client. ARM, I don't expect any problems at all. At least ARM Linux should be, from our perspective, exactly the same as x86 Linux. Mac, there could be some minor linking gotchas, but still, I don't really expect any. See, I'll assign MatCloud on that one as well. Okay. Okay, I think that's about it. Short stream today, but we, made progress, got back in the habit of streaming again. Well, can't call one stream a habit, but we are streaming again. This might be the last stream for a while, honestly, because I said the remaining work here, don't really want to do it on stream. I might do one more this week just to explore the doc stuff on stream. But otherwise, I'm going to be out of town in June. And hopefully by the end of June, we'll have the Rust client fully published and ready to go. And we can move on to, well, another thing we need to do with the Rust client is benchmark, write some benchmarks and do some performance work. I suspect it's already fast enough, but it might be nice on stream to do some benchmarking and performance work. It's a good topic for streaming. And also, I just know the client could be faster. But compared to things like the Ruby client and the Python client, who cares, right? Rust is going to be way faster no matter what we're doing. Haven't made any mistakes that monumental that it would be slower than those clients. But, if you're writing a Rust client, you expect it to be fast. So there's also the inefficiencies in the Rust client are around allocation and also around multi-threading in a way that is kind of fundamental to the binding strategy we're using. That multi-threading we can't get rid of because the TB client library runs its own event loop on another thread. So as long as we're using the TB client library in the Rust bindings, we're always going to be paying that huge, not huge, but relatively huge context switching cost to jump to another thread for every request and every response. which is not amazing, but also not too bad. Like the inefficiency of allocation and context switching is way smaller than the inefficiency of network requests and then actually writing and reading from the disk in the database. So I don't know how much it's actually going to matter the performance of the Rust client, um, in the grand scheme of things. Anyway, my name is Brian Burson on GitHub Bureau, so my socials are there. I do this stream sometimes, but you can never guess when I'm going to be here, so it's always going to be a surprise. Maybe a pleasant one, maybe not. Who knows? I'll see you next time.